Today, one technology company is valued at over $4 trillion, a market capitalization exceeding the gross domestic product of most nations on Earth. It operates as the architectural foundation of the artificial intelligence ecosystem. 30 years ago, the blueprint for this enterprise was sketched in a Denny's diner in East San Jose. The three founders had no clear business model, limited funding, and within a few years, they would find themselves exactly 30 days away from complete insolvency. The trio consisted of Chris Malakovsky, Curtis Priam, and a microprocessor designer named Jensen Huang. Nvidia began as a hardware startup building components for video games. 30 years later, that same core technology serves as the foundational infrastructure for the global artificial intelligence revolution. In the early 1990s, Silicon Valley was focused on enterprise software. Personal computers were defined by Intel processors designed to execute linear, two-dimensional tasks, spreadsheets, text documents, and basic databases. Then, three-dimensional video games emerged. Standard personal computers struggled to render these digital environments because traditional processors were not built to handle the required graphical workloads. This chart illustrates the sheer volume of real-time mathematics required to render a three-dimensional space. Generating a digital environment requires calculating light sources, tracking simulated physics, and rendering shadows, all simultaneously, 60 times a second. The calculations per second rapidly escalate into the trillions. Jensen Huang saw an opportunity in this mathematical density. He theorized that if an engineering team could build a processor capable of surviving the chaotic, high-volume arithmetic required by a video game, that same processor could eventually scale to calculate almost any complex problem. Video games were a consumer application, but mechanically they operated as a forcing function. The medium demanded a scale of processing speed that the traditional technology industry had completely overlooked. Nvidia's first attempt to capture this market was a multimedia chip called the NV1, released in 1995. They secured a major partnership with the gaming giant Sega to build components for the Sega Saturn console. The strategy collapsed shortly after launch. Microsoft introduced DirectX, a standardized set of rules requiring developers to build three-dimensional environments using flat triangles. The NV1 was engineered to render curved surfaces. The architecture was entirely incompatible with the new industry standard. Out of 250,000 units manufactured, almost all were returned. Nvidia had to ask Sega to dissolve their contract. The engineering team was reduced, leaving the company with exactly 30 days of operating cash. Facing immediate closure, the remaining engineers began designing a replacement, the RViva 128. Lacking the capital to manufacture a physical prototype for testing, they chose to simulate the entire chip design virtually. If the software simulation contained a single error, the final product would fail upon manufacturing. The simulation held. The chip functioned upon arrival, generating enough sales to keep the doors open. Surviving this crisis embedded a specific operational reflex within the company. Taking extreme technical risks became their primary mechanism for growth. The capital generated by the RViva 128 funded their next major release in 1999. It was called the GeForce 256, and Nvidia categorized it under a newly invented term, the Graphics Processing Unit, or GPU. To understand the GPU, consider the mechanics of a traditional central processing unit.
A CPU operates sequentially, executing a few highly complex tasks one at a time. The GPU uses a different architecture. Instead of a single powerful core, it disperses the workload across thousands of specialized cores. This is known as parallel processing. It executes thousands of simple calculations simultaneously, drastically reducing the time to render an image. The architecture's efficiency attracted institutional validation. Microsoft, whose software standards nearly bankrupted Nvidia years prior, paid a $200 million advance to secure Nvidia's hardware for their entry into the console market with the original Xbox. Nvidia had engineered a workaround for the limits of linear computing. By splitting massive workloads into thousands of concurrent threads, they established a highly efficient method for processing dense data. Jensen Huang noted that parallel processing had applications beyond calculating pixels. The GPU was, in mechanical terms, a computational engine perfectly suited for processing large arrays of numbers simultaneously. In 2006, the company released CUDA, a software platform. This interface allowed outside developers to write code instructing the GPU to perform complex scientific calculations, opening the hardware to non-graphical applications. For years, CUDA operated as a severe drain on Nvidia's finances. The platform was functional, but the broader scientific and technology sectors had not yet amassed datasets large enough to require that level of processing speed. The application for CUDA materialized in 2012. A team of university researchers working on an image recognition project called AlexNet bypassed traditional academic supercomputers. They used Nvidia GPUs to process millions of reference images, achieving an error rate significantly lower than any competing system. Working alongside AI researcher Geoffrey Hinton, the team demonstrated that artificial neural networks could effectively scale. The technology industry took note of the specific hardware powering the breakthrough. The calculations required to simulate lighting and physics in a video game are structurally identical to the mathematical operations required to train a neural network. Both rely on executing vast matrices of simple equations in parallel. The rapid acceleration of machine learning was the direct output of a consumer hardware cycle. Decades of engineering GPUs to meet the visual demands of the gaming industry had inadvertently built the exact hardware required to process artificial intelligence. Nvidia's business is now centered on the construction of massive, interconnected data centers. These AI factories are engineered specifically to train and deploy the large language models utilized by the world's largest technology firms. Their processing architecture now extends into physical AI. Through platforms like Omniverse, developers use NVIDIA systems to simulate accurate real-world physics, training autonomous vehicles and robotics in highly detailed virtual environments before they operate in physical space. An enterprise that spent its early years fighting for market share in desktop computers now provides the core infrastructure for global industrial automation and computational research. The scale of this operation traces directly back to the initial meetings at that Denny's diner in 1993. 3 engineers identified a bottleneck in how computers processed graphics. By aggressively pursuing the hardware necessary to render digital entertainment, they laid the foundation for global machine learning. The architecture required to model reality for a video game ultimately became the architecture required to analyze it.